Amrit, can I say the amount of open windows you had on a computer? It really made me anxious.
Oh no, this is only after restarting 2 days ago. So you got the light version of it.
Okay, so since we've got a pretty small group and not everyone who knows each other yet, we'll give ourselves a chance to introduce ourselves. You want to start in the middle room with Charles? Way back.
Hello, I'm Carl. I'm a second year in the neuroscience PhD program. Interested in the lab.
All right, thanks, Charles. Okay.
Hi, I'm Priyanka. I am now second year PhD student in Lucina's lab. And I'm in neuroscience department. Hi, I'm Katrine. I'm a psychology student from Denmark doing my internship in this lab, which is going a month ago.
Thank you. Hi, everyone. I'm Lucina, as you know. We're having a special guest speaker today, and I will let him introduce himself in a minute. Go ahead.
I'm Jason. Everyone knows me. I've been with Lucina for 8 years. Started as a postdoc in Miami and still here.
Great. Taylor.
Hey everyone, former graduate student of Lucina's. I live in Atlanta and I do part-time statistical consulting for the lab.
Thank you. And Sierra.
Hey, Sierra Bainter. I'm an assistant professor and former and current collaborator with Lucina at University of Miami in psychology, and I'm a methodologist.
Thanks for joining. Myra.
Hi, everyone. I'm Myra, and I'm a sixth year PhD candidate in the psychology department at UCLA, and Lucina is on my dissertation committee.
Great. And we've got Lauren.
Hi, everyone. I'm Lauren. I'm a fourth year PhD student at UCLA. I'm usually in person, but today I'll be proposing my dissertation right after this meeting over Zoom. So, yeah, right now.
Wow.
All right, great. This will take your mind off it. And Katie.
Hi, everyone. I'm Katie. I'm a postdoc in the lab, just started this fall, looking at a bunch of developmental and mood disorder based stuff, and had just wrapped up my graduate training at UIC.
Thanks, Katie. Is that everyone on Zoom? It looks like it. So I think Amrit and I met in Nepal. Is that right? Yeah, we met in Nepal in 2019 at some conference, right? I really can't remember these days.
It's like brain behavior.
Yeah, I'm going to that again. It's in Chile.
Yeah.
So anyway, and he's actually been working or had been working with Shella's lab at the time. Is that right?
Yeah, I was a graduate student then.
Great. And so, so that's how Taylor already knows him and is now working in Berlin. Is that, and I got that right? Well, there you go, Charité. So
Yes.
you are here to tell us about what you do, and please feel free to keep it informal, and we'll probably ask what to think. And tell us whatever you want to tell us about yourself.
Okay. Well, thank you so much for letting me present. I'm excited to be here. I was here for a wedding, and then I was like, hey, I know that Lucina moved to UCLA. And eventually I need to figure out how to come back to America, otherwise my parents are gonna kill me. So
Well, you know, what about Berlin? It's a great city.
oh, I know. Oh, I know. Oh, I love that city. I actually grew up in Berlin as a kid
I didn't know that.
in the 90s. So I would have spoke fluent German. So I had a chance to go back.
Mhm.
It's been absolutely lovely. And this is the work I've been doing sort of post my my dissertation. It's a little bit further away from behavior and a little bit more math. But I don't think it's super difficult math. But so everybody who gets confused, please interrupt. I usually interrupt everybody. So if you want to interrupt me, no worries. Okay, should I start? All right. Okay, so yeah.
just stop it and restart it, sometimes it's like,
Goes to that.
stop the share screen and start it.
Okay. No, no.
Oh, is the internet went out?
Yeah, but they're still moving.
That's weird.
I don't,
So I'm using,
Edgerome, no?
oh, yeah, your room kind of does that. It kind of comes and goes, but it's back. Is it back for you?
No.
Yeah, the Wi-Fi on campus.
There's also MedGuest. MedGuest.
Medguest?
Yeah, MED, you see that one?
Yeah, I see it.
That usually works. Yeah, it'll just pop up and ask you to join and you say yes.
Okay.
Yeah. That one's probably better in this than in this building. Yeah, MedGuest is working for me.
Accept. Right. Back in this.
You might have to rejoin the Zoom. Can you guys still hear us on Zoom? Okay, we're just gonna redo the PowerPoint. Yes, entry room isn't as reliable. Oh, there you're back. Okay. Put you back in. Starting over. It's always a challenge.
Okay. Wait. Right side. Wait, why is that just frozen?
That's weird.
No.
Let me try to kick you off and then maybe it'll, Okay, so I'm gonna do that and then stop share and then can you start again?
Okay.
What happens if you just do your full PowerPoint?
Right, I think you have to just do something, choose options to share,
Where's
double click.
Oh, view options at the very top.
this?
Oh,
Oh, the second one.
there you go. Okay.
Okay.
All right.
That was-
Wait, yeah,
Yeah, okay, there we go. Now everyone on Zoom sees the screen, right, the PowerPoint? Good. Yeah.
Yes. All right, it's switching.
You guys see a pyramid?
I don't see a pyramid.
You don't see it here?
nothing.
No, we just see the first slide.
Okay, can you, okay,
You don't see any of these?
It's not switching.
No, it's saying underneath there, Zoom US is sharing your screen. There's like a tab there.
how about now?
No,
Can you sign out of that and then stop share, click stop share? Okay. Now, instead of share screen, just share the PowerPoint, you know what I mean? So go to share screen and then just click on like the open PowerPoint.
Right. I can find it.
Yeah.
it almost looks like it's like you haven't stopped sharing on your original.
Yeah, so stop share.
Right, but that tab doesn't exist anymore. That person doesn't exist. I don't know who or where that.
Do you wanna like log out of Zoom, like internally, like close all the tabs?
All right, let's close
Yeah,
all the
close
tabs.
yourself and then, or at least
Closing,
all the Zoom tabs.
closing everything.
Yeah, and then we'll get you back on. Yeah, okay, and then rejoin from the original link if you can find it.
No, that's fine.
Okay, yeah, now you guys don't see anything, right, on Zoom? Okay, so we'll go back to, sorry, this is always trickier than it should be.
It's okay.
Yeah, you're back in. Oh, I gotta let you back in. Okay. Now you're back in. Now we'll let you share again.
All right, share again.
Yeah. Okay, now
Okay.
delete.
There we go. There's 3 Amrits up here.
It's usually what happens. You just keep multiplying. Gotta say.
How about now with that, where you guys see some
Yes.
changing PowerPoints? Yes,
Yeah, it looks like it's working.
Do you see the pyramid?
Yep.
All right, let's start. Okay,
Now we'll go. Thanks for bearing with us. There we go.
okay.
Okay.
All right, let's get into it. This is my little neural abstraction pyramid. Helps me kind of start thinking about sort of the data types that we're working with and the different modelings and approaches in trying to understand the sort of biological measurements we have. You probably are more, I mean, you're probably familiar definitely with the action potential and the intracellular recordings. And probably people in this lab are working with fMRI, I imagine they're working with fMRI,
Yep.
okay. And so the bottom of this pyramid, it's just mostly just sort of neurons, and as you're kind of going up, you're sort of getting activations of multiple neurons, multiple populations, and it becomes more from neurons, sort of a network kind of activity. And kind of at the bottom of the pyramid, we have kind of measurements of everything, so we can make nice equations and nice theories. And then at the top, things are kind of a little bit more incomplete. We don't really know what exactly is going on everywhere, but we're still trying to make, you know, representative theory high up on the pyramid. And so my goal has been to use sort of algorithms that are data driven to learn ordinary dynamical equations and systems that sort of represent macroscale dynamics from data, rather than sort of predefine all the variables and try to construct a complicated system. It just allows us to use our complicated tools that we have these days to sort of find a system for us and then try to examine it that way instead. So the positive of this is, of course, it lets us fit the actual measurables that we have. And of course, the drawback is we lose some sort of interpretability. If you had like a full, you know, Hodgkin-Huxley neuron, you pretty much know everything that's going on. We don't have that, especially also because the model will just fit the data, and it's not fully clear always if the model is a biological plausible or, you know, it's not. So you have to be kind of careful with that. But anyway, so we're trying to construct some sort of dynamical system for fMRI network activity. What I call network activity is basically you take sort of the raw bold signal right here and you sort of parcellate it in different atlas regions. And then I do the most minimal pre-processing possible, because all my algorithms are trying to find sort of structure. And if I kind of put weird pre-processings like global signal regression, then my algorithm starts changing a lot. So minimal pre-processing, just a bandpass, and then I just average these regions, and then I just normalize it by z-scoring it. So that's just centering and making the standard deviation of the signal bounded. And I took HCP data here to sort of, you know, because HCP just has so much data, and I took all the rest and the task and the left-right scan and the right-left scan, get it all together. You get about 8,000 time points per individual. So I thought this might be enough to train individual models if I wanted to test that, which it was.
So why combine the task and rest instead of just, you know, task from a separate?
Well, okay, so multiple reasons. One, I don't think it's easy to describe the system without having all the components. So, I mean, the other really annoying thing about trying to sort of represent fMRI network activity is that you don't only have the network activity, right? You also have whatever the person's thinking in their head at the same time. So there's a response to whatever is going on, and then there's also some sort of dynamical system that seems to be bounded based on the structure of the brain. So you have both of these two things. And to really study it properly, I think you need to do rest and task. Because whenever I think I understand rest and then I apply it on task, everything breaks down and then I start over again. That's what's been happening.
Is it like you use different kind of tasks or it's just one kind of?
I took every piece of data I could get from HCP.
Okay.
So there's like, I think 9 tasks,
Okay.
like language, gambling, working memory, social. Don't ask me what all of them are. I know only working memory well. But yes. Then the other thing I needed to do is I needed to have a description of, the network structure. So this is the global structure. This is just tractography. So the HCP has the DTI, and you can process it, and then you can basically go through software and estimate sort of fiber bundles between regions here. And so you have sort of this macro scale network structure, and you have this macro scale network activity, and we want to somehow find a way to go from sort of this network structure to the network activity. And this has been done for about 10, 15 years, maybe 15 is a stretch. Let's say 10 years. It's been done for about 10 years. And this is a group of models called brain network models. And this framework, basically what they do is they write out the description of the nodal dynamics of each one of our sort of the nodes of our brain as a differential equation. And the differential equation has basically a function of the nodal dynamics of itself in its current time. And this is usually used as a sort of a relaxation function. So they would, for example, this function could be as simple as like just a negative sign. And then if you kind of squint and make the rest of this equation disappear, then you just have the derivative of x is equal to negative x, and that the solution of that's exponential decay, if you remember. So that's basically just saying if I'm really active, I'll just kind of decay to the baseline. And then what they have here in the middle term is the sort of the network term here, which is my activity is increased by some function of the structural connectivity times each one of the nodes. And then this is a function G, I should put brackets here. So there's some sort of function of the structural connectivity here, some form of intrinsic relaxation, and then some sort of function of the current input that's also coming in. And this is usually set to 0 for rest. And they add noise to kind of simulate this. And then they integrate this giant equation across this entire sort of network by predefining the structural connectivity. And then you basically get this neural activity, and then they put it through this balloon Windkessel model, which is this complicated model for an HRF response. And then they simulate something that looks like fMRI. And because you simulated it by integrating it with noise and random initial conditions, usually the signal that you have is not easily comparable with like fMRI that we have. And so they end up using metrics basically that they use that maybe you're familiar with, like dynamic functional connectivity or functional connectivity, some sort of summary metric over a long period of time to characterize the bold response. And then they compare that with the real world response. And then they're like, okay, we kind of have fMRI. And this seems really fishy, always did to me. First of all, you're integrating with noise. Second of all, you claim that you have an ODE system, but then you don't really even use it to predict. So what was the point of it in the first place? So I didn't like this framework at all.
Were you doing the modeling work with Cello before, or did you just start that in Berlin?
No, I was doing it before. The problem was they, I think, like the traditional approach more, and I definitely don't, because I think it has some bottlenecks. But basically my boss has built this giant platform called the virtual brain, where you can choose very complicated nodal functions. You can choose sort of delays or whatever, and you can basically use all these crazy parameters to focus and synthesize something that looks like brain signal. But I don't think it was a good method, so I did decide to go somewhere else. So I said, okay, first of all, let's get rid of the integral. There's no reason we need to work in the integral space. Let's work in the derivative space. And derivative space, again, we're working with task. So in task, we know the input function is close to 0. We minimize it, get rid of the noise. So we only have these two functions. And when we work in the derivative space, we don't have to worry about initial conditions because the derivative of initial conditions is 0. And the local activity, which will be independent of the fMRI signal, looks like Gaussian noise. So how do we fit the derivative? Well, we fit it like kind of like the old school scientists did. So you have a bunch of dots, and I want to draw a function through it. So I want to maybe, have a Taylor series expansion that fits a bunch of dots. But you're not doing this in the regular space, you're doing this in the derivative space. So there's this algorithm that came out, which is called Cindy. And Cindy basically is this nice Python package that you can basically draw functions in the derivative space. And so how that works, it's actually just regression. It's really, really simple. What you do is you compute the derivative of all your state variables. So here, each one of our state variables here is from a Lorentz system, but in more general, each one of your state variables could be, different brain areas, the activity of different brain areas. And then you represent that, the derivative of that, as a function of, the state variable itself, right? So what you do to do that is you write out sort of a library of different functions that can represent it. So for a Taylor series approximation, you can just, write it as x squared, x cubed, x to the fourth, x to the fifth, so on and so forth. You can just write the whole expansion out for an nth degree polynomial. And then, so for each time point, which would be the vertical line here, you would calculate x squared, x cubed, so on and so forth. Then you have this giant matrix here and this giant matrix here. And basically the idea is that this small matrix here, which is the coefficients, would multiply times the functions to represent the derivative. And you have these two matrices and you have one unknown, which is basically ax equal to b, if you remember your linear algebra, and you can basically solve it using regression or convex optimization. Here they do like a lasso with an L1 penalty and a reconstruction penalty. That's basically it. It's basically regression. And you're just basically fitting a function that is a library of a high order polynomial to the bunch of dots that you see. That's basically what you're doing. Does that kind of make sense?
Well, what's the goal? That's what I'm losing.
Sorry, the goal is to see if you can find an ODE system to just describe the topic.
Okay.
So then basically what you have to do is your choices as a researcher is you have to pick a library. And then once you pick the library, then you can solve for those coefficients. And then we can see how those coefficients kind of compare to the functions that we currently think are there for the ODE dynamics. And then you can also use that function to predict and stuff like that. So the easiest thing that I did here is I made my life easy, and I also got rid of this green function right here. I just, just if you work enough with these ODE systems with fMRI, everybody just has this -1 relaxation term. So I just put that in as a constraint and then said, okay, just find me this coupling function that is the network interaction. That's what I want, because I'm also going to be solving for the coefficients of the structural connectivity or the effective structural connectivity that it is using to fit the data, so that I can know that I can compare that with the real structural connectivity. Anyway, so you pick this, and then it will solve. Basically, I force this diagonal on the first term to be all -1, and then it'll solve all the other coefficients. So how do you evaluate this?
Wait, I'm sorry, what's the input again? What was that size input? Just some variables that you're saying creates.
So the input, yeah, no, the input is just literally this. So you take the raw fMRI signal, average it, and get brain areas over time, like parcellity, ROI time series, and then that's the input.
All the time series at once.
Yes.
Okay.
So this is huge. It's 100 brain areas, 8,000 time points per individual, times 447 subjects.
And you're just trying to fit a bunch of derivative functions.
Yes.
Across the entire brain at once.
Yes. Perfect. That's it.
Amrit.
Yes.
So I guess I understand the derivative, but so is, so there's no original signals here. It's like just the derivatives of the, so like a finite difference, you know, how we calculate those, like the difference between time 1, time 2. Full
Yeah.
signal, is that how the derivatives are calculated? Okay.
Well, the package, I think, does like a 9th order difference formula, so it's like a
Okay.
order, but I mean, in theory, it's the same thing. But yeah, so you approximate the derivative, you have the measurements, of
Got
course,
it.
and then you calculate the library, and then you get the coefficients in the library to fit the function. Okay, so how do you evaluate this nonsense? Okay, so, well, if we have a model for the derivative, it should explain the derivative. So that's a minimum. If it doesn't fit that, you shouldn't believe anything. The second thing that we want to know is we want to evaluate is how well these coefficients relate to what we know as in brain structure and structural connectivity, and so on and so forth. And then the other one, what we want to do is maybe we want to have a metric to compare with sort of how previous people compare it with, so you know, I can trash the competition. No offense.
Say, you know, Petra or Victor or whoever, virtual brain people, like, what did they say about your proposal? Like, I'm sure they had defenses of their, you know, approach. So like, what were their reactions?
Maybe I should finish and then go
Okay,
there.
all right, well, yeah.
Because it'd be hard for me
Yeah.
to explain how they reacted to it without showing you what they reacted to it.
Okay, got it.
Okay, so one of the methods that I wanted to evaluate the model is, you know, I want to be able to say that I have been able to predict the derivatives. How do we do that? So here, you know, I have one ROI, x56, whatever, right? And you have, you know, this is one x vector across all space. This is all time, right? So you can take all these polynomial coefficients like x squared, x to the n, so all my polynomial coefficients, compute this vector, and then basically predict the derivative. So for each point that you get, for each x you give me, I can predict the derivative. So then I can calculate the actual derivative, and then I can compute what the derivative according to the function is, and then I can compare those two things. So here, there's just a sort of a example how these two kind of fit, and this looks kind of nice. Would be great if they all look like that. And then here is basically you start with the initial condition, and then you integrate the two signals. As you can see, they kind of stay together for some time, and then they kind of start drifting away. So this happens a lot. There's a lot of integral drift because I picked one initial condition and drifting. So it should fit the derivative better. It fits some of the integral, but then we'll start drifting away. Okay. The other thing that you want to know is, if I take this polynomial and then I integrate it with noise, can I reproduce functional connectivity? So this is the sort of the traditional way that they test these models. Can I produce FC? Yeah, you can pretty much produce FC. FC is not that hard. I also have to use this hyperparameter where I set my diagonal relaxation functions to just to -1, but then I can change it to a different number. And basically what I get is, this is kind of confusing to go without before going below, but I can get really high correlates to the DTI, like over 0.6. And I can get really nice correlations to my synthetic FC too, which is like 0.9. But in those realms, the derivative does not fit that well. But in the realms that the derivative fits well, the FC and the SC do worse. So that's kind of annoying. So I picked sort of the middle value to sort of show you all my results, which is around like 0.5 per K. So I gave up some of my nice derivative and some of my nice structural connectivity, but I couldn't really get the best of both worlds. The number of polynomial order does not change too much the results. So, I use the 7th order, but it doesn't change too much the results. Okay. So what I really get right now is this really nice structural to functional relationship. I can measure an individual's FC, I can measure their DTI, and If I take the algorithm and ask it to, you know, take the functional signal and give me a structure, then I can estimate pretty well. These are my first order coefficients of my polynomial, and they match the DTI pretty well. Moreover, if I take this and I take that function and I simulate it, I can get functional connectivity really nicely. So there's this really nice relationship between the structure to the function related with this equation. And this is not exactly fully new. This has also been able to do with TVV models. The nicer thing is this one just is kind of simple to do. So, but you can get this nice relationship, which is, I don't know if this is why I would just use this to justify that my algorithm's right, but I think that this whole idea that there's some sort of network model is right. If you look at the derivative, I can get, you know, for resting state signals, if I take what this is a distribution of each ROI. So I take, you know, the entire time scan, which can be, you know, 300 time points or 1200 on the rest, and I correlate that entire prediction with my measured derivative. I get, you know, a correlation over 0.4, except for a few brain regions where I do really bad. And the brain regions I do terribly at is where we also have bad signal, except for the foot region, which I don't know why it's bad, but, you know, the frontal lobe, temporal pole, these are the regions it is the least predictive of. But the rest of the brain, it's able to capture the dynamics pretty well. It also is able to get it across individuals really nicely. So I will train on, like, I don't know, 200 individuals and predict on the other 200 their derivative. And, you know, so it's the same function, but it's able to, you know, capture brain dynamics of completely other people really well. The integral is not that great. It gets worse the longer I integrate, obviously. But even at the start, there's a huge variance. I have a couple reasons why I think that, but I also didn't train for it. So I don't know, I might just throw this away. I don't think this is going anywhere. But the more important and more interesting stuff are what is the function that I actually solve for? Because there's a lot of unknowns of what is this ODE system? How does it look like? And my whole motivation for this problem is that this technique gives you some insight that maybe wasn't previously there in this ODE system. And so what you get is this really nice thing is if I take the DTI structural matrix and I correlate it with every order of the polynomial that I have, I get this really nice inverse relationship where only the odd degrees are present, and they have alternating coefficients. So it's positive and negative and positive and negative. And if you remember your Taylor series, if you have like an odd function for your Taylor series, then you have basically something that will cross the origin from negative to positive. You have an even function, right? It bounces. So you have this nice odd function that looks kind of like a sigmoid, close to zero. So this, I graphed some other sigmoidal functions that they use, and it's kind of between logistic and tan H. So it's a nice sigmoidal function of the structural connectivity. And I was pretty happy about that because this kind of looks right. And if I add the sort of the network signal with the relaxation signal, the combined dynamics, which I get, is this complicated looking thing right here, where at the very close to the origin, I have this little tiny humps. So how this works is a phase portrait. So this is X and this is the derivative, right? So if I'm here and I'm positive and I try to sort of give a little bit of positive push to the system, then my derivative is negative. So it's pushing me back towards the origin. And once I cross the zero crossing right here, right? Once I cross the zero crossing, then all of a sudden my derivative becomes positive and I shoot up and then I come back down. So basically it's a threshold to start the system. And once you have it, then you have like an event. So what that would look like is similar kind of to an HRF response where, you know, when you start the system, it'll go up really high and then it'll kind of decay with a little bit of a threshold. So I'm thinking that this nonlinear function is the HRF that's kind of buried in here. And that's kind of where I am at with it.
Like the HRF for rest.
So there's still events happening, right? So this function basically is saying that if I'm here at 0 and I give enough of an input, you'll have an HRF. Does that make sense? But I need to test this out better because obviously I haven't shown you any impulse responses here. I've just showed you the phase portrait.
Okay, I guess I'm just because we don't consider inputs during rest.
Right. No, there is no inputs here. This is just the phase portrait, right? So this is just the
So you're modeling spontaneous activity, right?
there's fun well, there is activity here that right it's canceled out here. It's canceled. That is seen as noise, right? So the idea is that there is structure from other sources, right? So there's the network activity and then there's activity from other sources. But if I throw enough rest signal where the other source activity looks random, so there's no structure compared to the network, it will minimize that and learn the other part of the dynamics, right? Which is the network part. So then I graph the phase portrait of the network component. And I basically, so then the phase part of the network component, if you push the system from the origin further enough, then you'll have some sort of an activity. Does that make sense?
Yeah, I mean,
Please ask more questions.
why I think you're coming at it from a modeling point of view rather than. I mean, I understand what you're saying. It's not input, but more of a start of the system.
Yeah, I mean, I'm hoping to, I have the working memory data on there. I'm slowly working up to it where I'm trying to get, basically I'm trying to put in an LU input train here and try to get the HRF response that they see. And then I was going to try to decode. That's where I was trying to go with this. That way I have network component, that way I have the right input component, and then it should do something.
Amrit, for my help in terms of the equation, just so I have this right, going back to, you're saying Cindy is a sparse regression framework. If
Yes.
I have this, so the structural connectivity is setting the coefficients of the model. Is that what the structural connectivity is being used for?
No, the structural connectivity is used to compare what my coefficients look like.
Okay, so but the coefficients are actually estimated from the derivatives of other signals in the network?
Exactly.
Okay.
So the coefficients I get an ODE system, and then to characterize it, I'm like, okay, it has to have this weird structural connectivity in it somehow. And when I look at it, it's like, okay, yeah, it is in there. There's a quite high correlation in the first, third, fifth, and seventh, and they're alternating signs, so it looks like an odd function of the structure. Obviously, it's not a perfect fit, but because it's an algorithm, right? But the idea is that there is some sort of function of this thing that could be representing brain dynamics.
Okay, and so the polynomials are just like the square of the derivative, the cube of the derivative of the other signals, right? So
no, not of the derivative, of the actual signal,
okay, so the predicted outcome is the derivative, and then
literally x squared, x cubed. You take this x and you square it, whatever, and then you get the coefficients for each high order. So these are the first order coefficients, the second order.
Time point you're doing that?
For each time point, I can predict.
From the time point before.
For each, no. You don't need the time point before, right?
You
Because
use
you're
the
taking- I'm taking X and I'm predicting derivative,
of X.
yes.
I mean, this, just so we know, because we don't do modeling work, like, what are the standard ways of evaluating models? Are you doing what people would normally do in the field, or you're proposing something different?
Well, the standard way of doing it is the functional connectivity thing,
Okay.
but then I railed at like 0.9, and I was like, this is not useful.
Mhm.
Also, there was like multiple models that were doing really well here.
Mhm.
And I also thought FC wasn't that useful. So I made this new metric, which is the derivative, which I think is way better. How do they like it? Well, okay.
Yeah.
All right, so I've gotten mixed responses. Some people love it, other people hate the crap out of my work. The people who dislike this work dislike it because I took all the advantages that they argue for generative models and then did not use generative models. And that is basically, hey, let's, define everything nicely. We have the structural connectivity. We have all these things. Let's construct a system from these primitives. And then we can like make meaningful interpretation. And then if somebody has, sickness, we can change that part in the brain and then see how it goes, right? But here, since I'm learning everything, they're like, it's not, it might be just a mathematical construct, but I'm like, it's coming out kind of nicely, too nicely for a mathematical construct. And also, like, I don't have a problem. Like, you don't have a problem from taking structural connectivity, putting a bunch of equations, making a synthetic signal, and then comparing it to bold in a weird way. Why is it weird for you to just take bold, shove it into an algorithm, give me a structure, which is static, which is a lot easier to compare, and then compare that? So I don't really have a problem with that. They definitely did.
Has it gone through reviewer comments and whatnot, and like, are these papers out, or?
I'm submitting hopefully December. So
Curious to see what,
we'll see how this goes.
I have two doubts about the derivatives.
Mhm.
You were talking about odds being inverse. So does that like signify that the system would be inactive or active since this one is like inverse? So like I don't come from this background, so for me to understand it, I need more the understanding of it. So when you talk about the inverse relationship at odd derivatives,
Yeah.
what do I expect the network to look like? Should it be active or inactive?
Okay, let's work with this graph. This one's the easiest one, I think, to kind of understand stuff. So forget about what's going on, in the tail end, like just imagine the middle is just a perfect line, right? So that's basically saying, and this is the network component. It's like, let's say we all are a network, but we're not all connected, So, some of us hold hands, some of us don't, okay? And if you're holding hands and my activity is going up, okay, then a linear line basically means here is that if I'm going up or down, my friend is going up or down. Okay. What happens when you're getting closer to the edges of this, where it's sort of curving, it's a sigmoid, is basically, hey, I really want to go up, right? So that's my X. I'm really active, but this system, because it's biologically constrained, cannot become more active or even more crazily, trying to get active because there are biological constraints. So it kind of flattens out. So that's why people thought it was a sigmoid in the first place, because we knew it was linear kind of close to the origin, but then closest to the edges, it would kind of rail, right? And that was just for the network component, right? And then there's multiple parts of this function. So that's how this stuff starts looking crazy. What was your original question?
Yeah, so it's about the initiation component that you have. So you cancel that out along with the noise. But from my understanding from molecular and cellular single neuron, that model that you were showing. So basically each neuron has its own baseline, its own threshold. So assuming like, I don't know if people have studied like if each network has its own baseline or threshold.
Yeah.
So and compared to controls versus diseased,
Yeah.
won't the two populations have their own baseline? So in that situation, won't that component be of use?
Yeah, so, okay, wait, I like had three thoughts and I forgot what your first question was. Okay, so in terms of fMRI being a wavy thing versus, spontaneous events, I think Taylor can jump in on that since he has a paper on 3 waves in fMRI. It's a little unclear, I would say. There are people in the field who absolutely believe in event-based fMRI, right? And there's a couple of reasons why you have this idea. First of all, if I make you do a task activity, it's clear, like if I make you do a task, the thing turns on. Okay. If you do something called point process, if you Google Tagalucci, he's a complete believer in this point process activation of fMRI, which means that the signal is really only interpretable very, very high from baseline, very, very low from baseline, and then everything else is unclear transition. So he believes this very intense this versus this. And then there are other people that believe a more wavy nature of it because it kind of looks like a wavy nature and you have these periodic patterns happening. Now, I honestly, unfortunately, think that it's both of these things are happening at the same time, which is why this is a bloody mess. So yeah, I don't know. I mean, here it basically says is that if you don't push the system further enough away, it will just kind of come and just settle down at 0. I kind of do believe that, but I don't know. I mean, I think I need to spend more time with the impulse response because if I don't get the impulse response correctly, then I don't fully believe this. And I also don't know exactly where to put the input. I've put it nicely in this part of the equation, but it could be here, it could be here. I don't know where it could be. So it's not fully clear. Yeah. But what is nice is that I can build really good systems. I probably should have put this slide in. Is I can basically build individually specific models really, really well, which means that for clinical use, this is going to be great. If you want to, make an individual FC and you care about that individual's FC, I can take their fMRI data, give me one ODE system. That ODE system is closer to their own measured DTI. It's closer to their own measured functional connectivity, and it's also the derivative is closer to their own derivative than if I use the ODE of a random individual. So there's this nice individual specificity, which means that I haven't worked with clinical data, but I probably could make very nice clinical specific models for this.
The virtual brain was set up that way that you could add your own data, right? Like your own
Yes.
to it. So you could I don't know. Are you just like not doing virtual brain stuff at all? Like you're just like away from that, or are you like?
So the original part was I was hoping to take the virtual brain systems themselves, the equations that they have, and then solve for the coefficients. But that actually became kind of hard to do, like methodology wise, and I didn't trust it fully. And I also was like, okay, the most basic way of inverting this problem is doing regressions on polynomial like coefficient. Like that's like baseline, the simplest thing you can do is do regression. So I was like, okay, I'm going to start here. Yeah, that's where I'm at.
So are you, sorry, go ahead.
Oh, Amrit, could you take us back to that the introduction to the Cindy estimation with the warrant system? That right there. Have you because like when we're talking about derivatives here, like just the differencing of the outcome, I think of the econometrics literature, how in ARIMA models, right, when you're forecasting, oftentimes they'll model like the derivative and as a function of other variables, and that gets extended to multivariable systems and like multivariate autoregressive equations like vector autoregression, right? So have you interacted with that literature? Because I'm seeing a lot of overlap here.
I'm
In
not
terms of,
fully sure what you're referring to, but if you want to send me an email, I'd be more than happy.
You mean
Yeah.
like Granger, Taylor? Like in Granger uses
Oh.
vector autoregression? Is that the kind of thing?
so Granger is used on vector autoregressions, as they take the coefficients to estimate like the quote unquote causal impact, but just the whole modeling, because the motive, if you study like econometric time series analysis, they're obsessed with modeling dynamics of time series through really the motivation, they don't call them, because they're discrete instead of differential equations, they call them difference equations. So like the discrete version of differential equations, but like they're doing from what I mean, and I'm not an expert in that field, I just know that there's a lot of the terms that I'm seeing here are very related to that literature.
Yeah.
And I wonder if it's related to the way you're fitting this with a Cindy model might be analogous to like a VAR with sparsity in the estimation. So I can send you some literature on that, because it's been a while since I've looked at it. I'm not an expert by any means, but the goals and the way the problem set up look very similar.
I think they should be really similar, because I do know that difference equations and ODEs can be translated from one to another. I have seen that. It does make sense to me why you would also say that this is similar to VAR, because that's what autoregression, they create a function, right? I think that, there definitely should be parallels. But it's just basically function fitting and then trying to understand what that function is. That's basically what this is. And then trying to convince the people that I don't have a mathematical construct in. The brain actually works like this. That's another tall order, but I'll figure it out one day.
Right. So I guess, do you mess with that sparsity term in the Cindy to make sure? Because I know when you get into higher.
Yeah, so the sparsity term is
crazy.
basically this hyperparameterization. I didn't fully explain this properly,
Okay.
but basically, because this threshold is set, and when I change the relaxation coefficients on how sparse these things can be, it basically is. If I have very high values, basically I have what I have here is so on this end I have very sparse solutions. So in very sparse solutions, I have very good fits with my structural connectivity, which makes sense. But then my dynamics kind of goes to crap. So if I put less sparse solutions where I can loosely fit the dynamics, then I get a much better fit to the dynamics, but then it gets worse towards the structural connectivity. So that's the trade-off here with the sparsity.
Right.
Does that make sense?
Yeah, I mean, I keep thinking, because usually I've seen in the literature that adding polynomials can cause a lot of overfitting problems. Have you looked at like adding using splines or something? Because those are traditionally ways to fit nonlinear functions without all the polynomials. And I mean, I know you wouldn't get an equation from that, but you might be able to probe the.
I took out parts of the polynomial, so I tried like seventh order,
Okay.
only the odds parts of it, or so I was testing, and it does pretty decently with just odds. So I don't need any coefficients really.
Interesting.
And it was fitting better. But yeah, I was also like, I think right now I'm also fitting the entire diagonal to a single value, but that I can change too. I realize that if I change these values, it fits better. I don't really know exactly how to get maybe the best function out of it, but rather than going down that track, I was trying to maybe characterize it with the other parts that we know have to be true in in fMRI, which is like, you need to have an impulse response that looks right? Like whatever dynamic system you pull out. So I'm trying to get those parts to look more right. Then to find ways of getting a better fit or a better solution. Because I've spent too much time on that already.
Right.
Try this on other data,
Huh?
try this on other data.
Yes, so I tried it on other fMRI data. I don't know if that counts as other data.
Yeah, because of scanner is unique.
Yes,
Was this,
Yeah.
they fixed the noise or not?
no, you use those things, you get all sorts of nonsense. But I had, why didn't I keep
Wait,
it on
if
this
you use
slide?
ICA fix.
All
and
of
it
that,
doesn't
you
work?
you just get nonsense. You literally,
little
if
concerning?
you mess with the pre-process, okay. This thing is so sensitive that when I use HCP's surface files, I wasn't able to get a generalized equation. It was only when I did it to volumetric and you basically have to register each parcellation to the individual on the volumetric side, I was able to get a generalized system. So what it definitely showed me is that a lot of pre-processing, it definitely needs to be, I mean, nobody knows what the right pre-processing is, right? That was also super frustrating. So I had to change it a bunch of times.
So doesn't the signature just modeling noise, or it could be just modeling noise?
Cause yeah, the HCP data is 90% noise.
It's 90% noise.
Well, there's a lot of pre-processing you have to do to get any meaningful.
When you do the ICAP noise, and it takes out 90% of the component.
Yeah, but it looks really weird. I don't like how their signal looks after. It looks really sketch.
But it's noise, like, I mean, when you look at it.
Because
Like, obviously not neural signal they're taking out
well, okay, with which one are you talking about? The after minimal process?
with the ICA fix.
I don't like the ICA fix step. I don't think that step is right. I really don't.
You don't think the ICA
No, I
fix is
don't.
right?
I have very problematic.
Well,
Also, the global signal. Also, the global signal.
What's that?
Also, global signal. I just is completely nonsensical.
No, we don't do the global signal.
Because what it did for me is I started getting negative coefficients on my polynomials. Well, I get negative coefficients, but only on my higher orders, not on my first order, right? So,
But don't you think that might be a problem with your model and not ICA?
no, I don't think the
No?
ICA thing is right. The signal is not right. Look, I mean, like,
Well, no,
I can-
what's commonly done, like
hold
in
on.
this literature, when there are people are, using it on the virtual brain or something, for example, like, is it common for them to use the HCP pre-processed data? Or is it
I
not?
definitely pre-process it exactly
The
how
way
I
that-
like it.
Okay, so that you're doing what your lab would have done. with
But
your-
not because I agree with them, but because I
Yeah.
think that's.
Well, I
the-
mean, to them that what you're doing is legit. You're doing the same, pre-processing that they would have.
Yeah, let me get to, where is my pre-processing stuff? So I tried a bunch of stuff. And I got a lot of nonsensical answers from most stuff, honestly.
Wait, which one looks nonsensical to you?
These two look weird as hell. Why this is HCP's ICA clean, whatever they're
That
fixed.
looks correct. Did you order the nodes according to network structure?
This is exactly that. It does not look correct.
Wait,
I do
what
not think
atlas are
that's
you
how,
using?
I don't think that's how it's, I think this is how the signal is supposed to look like,
Which one?
The original.
the original.
That one?
Yeah.
Where everything's connected positively with each other?
Yeah. I think that's the signal. I don't think they know what they're doing here. Because when you look at the algorithm, filtering honestly has the best coefficients I got, but it wouldn't generalize until I switched from surface to volumetric. I couldn't get this to work, the original.
Wait, what parcellation are you using?
Decay and Kiliani.
Yeah,
The PCA, okay, so like PCA, so if you do PCA, it puts everything in the same space. So then you can predict the derivative really nicely, but then your coefficients look like crap. And then, so each one of them has their sort of drawbacks and whatever, but the ICA stuff, like I couldn't get anything to like do anything.
I'm just having
And
a hard
then
time wrapping my mind around that your algorithm is the final determination of.
it's not,
brain
I'm
damage
not
look like.
claiming that, but I think saying that my algorithm works the best when you don't do anything to data and you just filter it sounds also right. Why would you need to do some crazy stuff? Like, what did you do to the signal to go from here to here?
Because, well,
Well, all you're doing is
biologically,
modeling what's.
Yeah, but you
what's
don't know the
poison.
ground truth, right? Like if they showed me, okay, yeah, I say he's removing that properly, I would have believed them.
but if
but
we look
like
at a
they-
resting state scan, we know the brain's not positively correlated with each other.
I mean, a lot of it is. It kind of is all going together. You only get these negative correlations when they do global signal regression and stuff, right?
No.
These things are,
Well, you
a
still
lot of
get
them.
them, they're just not as extreme.
Yeah,
It's
they're not
just
as
they're
extreme.
shunted.
It's just they're not, there's around zero.
I don't know.
Well, you're gonna have a hard time convincing reviewers that all of their HCP processing pipelines are wrong.
Well, I mean, I'm able to get, the same answer with the same similar processing. This was published in Scherner. This was 2017, 2018 in my lab.
Mhm.
And this data set, what he, processed it for was to get multimodal EEG to fMRI to look correctly. And so, this is a completely different justification why you didn't need all of that nonsense in the first place. Because, he had to fit EEG to fMRI. So he did the processing so you could fit EEG to fMRI.
Wait, what does fMRI look like correctly though? I don't know.
I claim it's this. I don't know. I don't know.
That's,
I claim it's this. I don't think you need to do ICA fix. And also ICA fix doesn't remove that much either. Like,
have you done ICA fix?
yeah, using melodic.
So if you do it yourself, like if you train and look through the components and like make sure it's appropriate for your data set, it's different for every data set. right?
See, but that was already getting all the questions. That's why I didn't see it.
It's like
Every data set has a different amount of structured noise.
Yeah.
Every scanner has its own unique structured.
I
noise.
believe that. I totally believe
For
that.
sure.
Yeah, so that's what ICA is removing. That,
But what do you? I don't think it can tell what noise is. I don't believe the algorithms.
you never looked at ICA components and say, oh, this doesn't look neural and this looks neural.
Like this is
Yeah, because there's noise all over the place. And look at like the graphene ICA component, there's stuff going on, or like across the whole thing.
Yeah,
You're gonna like
yeah.
introduce like weird like nonlinearities in it as well.
I mean,
Well,
I don't
you
know,
can't-
I've just seen a lot of ICA and I just know that about 80 to 90% of most data.
Well, that's because actually also the people who use ICA, they believe in like this cocktail problem that solves the brain, but that cocktail problem was,
No,
written
I
for
don't think they
cocktails.
believe that it's absolutely cocktail.
And then I'm
It's just
like,
one
I don't
way
believe, I just
to
don't believe
structure
it. I don't believe it. I don't believe it.
Okay, I'm having just a hard time. Believing that this algorithm sets the standard for what brain data should. look
I
like.
never said that. I never claimed that. Never claimed that. I did say that too, this one also showed from EEG fMRI. And that maybe should, I mean, somebody needs to do a study on, what is the right pre-processing for all of this.
I mean, there's 100 studies on different pre-processing pipelines, and there's no consensus.
There's no consensus.
There's no consensus on one pipeline, but there's a lot of consensus around the group of things you need to do to data to believe what is coming out the other end. So a lot of these papers, I think what there's really no consensus on is global signal regression. That one is just like nobody agrees, right? Because I think you throw out a lot more signal than noise. Some people think you throw out a lot more noise than signal, right? So there's no consensus there, but there's a lot of consensus about just like little things like all of like the Ted Satterwhite's papers about like the pipelines that involve, ICA, the ones that involve filtering, the ones that involve white matter regression. I mean, so I think nobody disagrees that you should regress out white matter signals, right? Like, I don't, or at least there's not a lot of controversy around it because, it just seems like an uncontroversial step. So here you're not even doing that, right? Like,
No, I'm taking what is considered HCP clean. Well, I mean, not like
okay,
the
so what
fully
is
processed.
HCP clean?
ACP clean is, okay, ACP clean is the fully processed. And then there's the MSM AII, which is the minimal process.
Okay, so what's which one are you working with minimal process?
The minimal process,
Okay.
the full clean, I don't know what they did.
Okay,
It
so
does
for
not
minimal
look like.
clean, what is minimal process?
Minimal process is all the usual stuff, motion regression,
Okay.
registration.
No, there's no motion.
They don't do.
They do MC, they do McFlirt.
The
That's
regular,
not motion correction, that's realignment. Those are two completely different steps.
so it's just the realignment.
Yeah.
No, they do McFlirt,
McFlorida is
That's-
realignment.
Realignment, it's not motion
but
correction.
they use it also to,
Do they regress out the motion?
yeah, I'm pretty
No, they
sure.
don't.
For the MSMAA, yeah, actually, sure.
I don't remember.
No, they don't.
I could pull it up.
I guarantee it. Cause in the ICA fix, that's where they regress out the first in 24.
This is the minimal processing.
The paper is more useful.
What is this release notes?
That's reference value.
Yeah.
Here we
Oh,
go.
there it is. Oh, the 2013. Yeah. I haven't looked at this in a long time, so I don't remember what they actually did.
The clean comes later, but the MSMAA is. Here, so
Okay, is that the figure? Okay.
brain distortion correction. Here, DOF.
Average aligned.
Yeah, that's realignment. That's not much. That's not
They
regression.
calculate the motion parameters and then they take
They
it out.
regress them later.
Yeah,
They-
I've looked through the code. I'm pretty sure we do it.
Well, I mean, they call it for motion correction. That's what they call it. But so they
Here, I don't know.
motion correction is
realignment.
to the single band. That's just the realignment. Yeah, but that's fine. I mean, it's just terminology. So they're doing yeah, they're doing that, but they're not regressing the motion parameters, right? Or they're not doing like the first in thing where you take the 24. They're
No,
not doing
yeah,
that.
there's none of that in the minimal.
Okay. So, well, they're doing realignment, but they're not doing anything else.
No, I think they do rigid body motion correction. I
Yeah,
don't, I
well,
don't know.
That's
what
realignment.
makes-
It's not, these are two regression of motion parameters. It's
Okay.
not
Is a
realignment.
different step,
Okay.
which they don't do, but
Okay.
they do realignment.
That is why you wanted the ICA to like see what that was and pull it out.
No, that's different also.
So well, they do minimum stuff, so that's, you know.
The ICA doesn't really account for. They do the ICA fix in addition to regression of the motion parameters in the HGP process.
In the more, and not in this minimal, in the,
In the ICA fix,
yeah.
so.
Well, in any case, I guess you'll have to convince the people that
I
not
think a
doing
lot of
these.
people use this version of HCP and publish, so I'm not that, you know, I'm not that worried.
Well, I
And
guess we'll see.
we'll see, we'll see.
Right. Well, it'll be interesting to see what comes of it. Thanks for.
Anyways, thank you for listening
Yeah,
and
thanks.
giving the feedback. I hope you are excited to do more science and
We definitely don't do any of this, so it's very educational for us to see what's going on with modeling. It's kind of a black box for us, because we're just working with like empirical data, you know, doing clinical comparison. Most of the lab is working with responses and and then, yeah, we've been mostly working with obviously HCP, some of the NPI data, but, you know, that then we're getting into the mind lesson brain connectivity. It's basically the same protocol about with 9 and 10-year-olds and longitudinal data and stuff like that. So we have not done any modeling
yeah.
at all. So
You can talk to Uber, sorry,
to
Uber.
I'm
You saw
sorry.
him?
oh yeah, he's someone in our lab who was rotating through, who's doing some of this work. He's not at the lab meeting today.
Gotcha.
Yeah. But what do you want to do for next steps? Like, what's the goal?
I don't know, publish, talk to people,
Do more work.
try more stuff. I think that every single time I try to get my model to do anything on working memory, it completely breaks down.
Well, working memory is included in your task, right? So it's one of.
Yeah, no, I mean, I have tried testing on it and I'm like slowly now I'm just like, okay, I think I need an HRF response. If I can't get an impulse response, like how am I supposed to go after working memory?
Mhm.
So I'm trying to get that to work. Because the moment I feel like I can be like, hey, yeah, I think I can decode your tasks,
Yeah.
behavioral
Well, then
better.
you have.
Then everybody
Yeah,
on
everybody-
this side is like, okay, yeah, I'm gonna listen to you.
Yeah, I mean, if you can
Okay.
predict task responses, that like probably mitigates a lot of other concerns.
Yes,
So,
yeah.
well,
Have you tried rest and task separate?
Yeah, so I maybe didn't explain this properly, but there's like all my,
oh, that's.
Is one better?
this is all the rest, and this is the
So they're.
the
pretty
task, so you
equal.
can see that there's a huge difference.
Oh,
in,
like-
Wait, rest, what is that? What's
Oh,
on
wait,
the
rest is way
y-axis?
better.
the rest is right there, obviously.
Rest.
So it's way more predictive in rest, and the blue and the orange are testosterone training,
Oh,
so
it's
it's
more-
unseen versus seen.
It does a better job in rest than task with that.
Yeah, by like a tremendous amount.
Okay.
So then I knew that, okay, something is going on
Hmm.
that it's clearly not capturing. And I was hoping that it was gonna tell me what that is. But to coax it out of it has been something.
Is this time? It doesn't reach time point, so it doesn't matter ordering, right?
It doesn't, which ordering?
The temporal ordering of the time points.
It would matter because a lot of the derivatives are computed over one time point. But yeah, I mean, it is multiple scans. So I throw each scan in separately and it just takes it all in and does the whole nonsense. The package is really nice to use, honestly. It does most of it. But yeah, no, they've been using it on climate science. If you ever need a crazy differential equation to describe stuff for you.
Well,
Climate science, that's what Taylor used in this
oh yeah, Taylor was doing that for his paper.
complex PCA.
That whole thing. Well, giving us a lot to think about. Thanks, Amrit.
Thank you.
For sure.
Thank you.
Fortunately, you came on a day when I'm basically going from one meeting to the next. So.
No worries, it's been a pleasure.
No, it's good. It's 5 minutes to stop by. Are you sticking around in LA?
I gotta leave by like the end of the week.